Okay. So just to let you know that you will soon get the information about the midterm lab exam schedule, and our midterm lab exam for EE340 is on 23rd March, and I will update the course syllabus and post it today so you can have a look at it. Okay, and this is from the registrar, not from us.
And the material, Doctor, what is
Yeah, material mostly we give the material. See, it's on 23rd March, right? So most probably the material will be the week before the week of the exam. Okay, I will put it in the syllabus. So anything else? Okay. So let's start our class. So let me screen share. Okay, so in the last class, we concluded our electrostatics, and then we started with magnetostatics, where we spent some time on understanding the source behind the magnetic field. And we have seen that it's the movement of charges. And if the movement of charges is a constant DC, which is a constant drift velocity of the charges, then we get only the magnetic field. Whereas if our current is an AC alternating current, then we will see that besides magnetic field, we also get the electric field. So now our magnetostatic is based on case 2A. So where we looked at different types of currents that can exist: line current, sheet current, volume current. This is the more generalized case. This is the special case of the volume current, and this is also the special case of the volume current, where this is the case where one dimension is almost negligible, and here where two dimensions are almost negligible. Then let's start here. So we are going to look at the main law, which is the Biot-Savart's law. So this is very similar to our Coulomb's law. So whenever I'm talking about the electrostatics, I'm going to give give a reference to our electrostatics, how this electrostatics and magnetostatics are similar. So here the governing law is Biot-Savart's law, and this is similar to your Coulomb's law. Coulomb's law in electrostatics. Okay, so what does this law is saying? Again, this law is an experimental law, experimentally observed law, similar to the Coulomb's law, and it states that if you have a current which is carrying in a wire, and if this wire is of length L, and this is the current carrying, and this is the direction of the current, then if I take a small elemental length of this wire, and this small elemental length is dl, then if I want to observe what is the magnetic field, the magnetostatic field, okay, so here magnetic field, I'm referring to the magnetostatic field, time independent field. At this observation point P, due to this small elemental length, is given by dH bar is equal to I dl cross AR over 4 pi r square, which is equal to, if AR, what is this AR? Again, R bar is the distance vector which is pointing from the source to the observation point. Okay, from the source to the observation point. And AR is the unit vector along this distance, along this line. And its direction is again from the source to the observation point. Very similar to the Coulomb's law. So therefore, this unit vector AR, so this unit vector AR, we can replace it because this is the direction of AR. And this unit AR, we can replace it with R bar, which is the distance vector over its magnitude. And if I substitute here, so I will get I dl cross R over 4 pi R cube. And this is for this small elemental length dl. Now, if I integrate it over the whole line of length L, integrate it over the whole line of length L, then I will get the magnetostatic field, which is because of this wire of length L carrying current I at this observation point P. Now, there is one thing which you need to notice. What is that? See, the magnetic field is proportional to 1 over r square. See here, the magnetic field is proportional to 1 over r square, which is very similar to the Coulomb's law, because in Coulomb's law also we saw that the electrostatic field is proportional to the r square, that is the distance. So it's the distance. It is inversely proportional to the square of the distance between our source and observation point. So here also it's the same thing. This is the same thing. Now this is the first point. Now this second point is very important. Now what does the second point? This second point is saying that your magnetic field, so where will it exist? So your magnetic field will always be the perpendicular. This is the perpendicular sign, perpendicular to the plane containing dl and r. Okay, dl and r. And remember here, dl, we are showing it in the form of a vector, because here the direction of dl will be the direction of my current. That this is what I'm writing here. dl is in the direction of the current. So here it says that if this page is my plane, if this page is my plane, and if this wire is residing in the plane, and this observation point P is also residing in a plane, then, so this is my plane. If both are residing in this plane, then your magnetic field will be perpendicular to this plane. So either it will be in this direction or it will be in this direction, but it will be perpendicular to the plane. This is an important property, and we know it. This is coming from this cross product. This is coming from this cross product. So this is an important property of the magnetic fields. They will always be perpendicular to the plane in which your source and your observation point is sitting or residing. Okay. Now this will become even more clearer when we take an example. Okay. So now in a similar way, we can extend the Biot-Savart law to the surface current and volume current. See here. So for the surface current, if this is my observation point P, and if this is my K vector, then H bar is integral over the surface, K bar ds cross R over 4 pi R cube. And for volume, it is integral over the volume, J bar dV cross R over 4 pi R cube. So this is the Biot-Savart law for all the three cases: line, surface, and volume currents. Now let's take an example. Okay, so let me say make it smaller so that I can see everything. Yes. Okay. So what is the problem statement? The problem statement is we need to find H bar at this observation point P due to the straight wire with current I as shown. So if you see here, this is a wire and this wire is of length Z2 minus Z1. So it's a finite wire. Okay, it's a finite wire and it is placed on the Z axis. See, it is placed on the Z axis. So let me first bring it up. Okay, so now let me annotate. So this is my Z axis. And now what is its locations? So this is my observation point P and this point P, and this is my origin, and rho is the perpendicular distance. See, it's the perpendicular distance. So that's why I'm extending this line downwards and then finding the perpendicular distance. So this is rho. And then I'm saying that this edge of this line is making an angle of alpha, and this top edge of the line is making an angle of alpha 2, alpha 1 and alpha 2. Okay, and now my elemental length is this one. This is my small elemental length, which is dl. Now in our case, I name it as dz dash because dashes are always used to represent the location of the sources, very similar to our electrostatics. And since it is placed on z-axis, so if I want to integrate it to get this line, it will be dz dash. In dl will be dz dash. And its location, it is at a height of z dash from origin. So this is required for integration purposes. And then the distance vector. So this elemental length is at a distance vector r bar from my observation point P. And this elemental length is making an angle of alpha. Okay, so these are all my problem statement. So let us start now. So what we will do first, we will first find the magnetic field due to this small elemental length using Biot-Savart's law. So what is the Biot-Savart's law? If you see here, dH bar is I dl cross r bar over 4 pi r cube. Okay. Now first let us find the dl vector. So the dl vector is nothing but dz dash, right? And what is the direction of the current here? Is upwards, right? So the direction of the current is upwards. It is in the AZ direction. So that's why dl dash is dz dash times AZ. Okay, it is dz dash times AZ. So this we got dl. Now the distance vector r. So the distance vector r, we follow the same rule or the same steps that we did it for the Coulomb's law. So to find this vector r bar, which is in this direction, I will first go from here to here, and then I will go from here to here. So what is this one? Yes, Mr. Saif Al-Zahrani, can you tell me what will be this vector? Yes, what will be this vector?
Is it minus AZ?
Yeah, it will be minus AZ, but what is its length?
Z prime.
D prime, right? So this vector will this one will be Z prime minus AZ. Okay, and what about this vector? Yes, Mr. Thabit, can you tell me?
Yes, Victor.
Yeah, what is this vector? Maybe
It's in
you
the
can.
row axis.
So it is home. It is what?
It's in the row axis.
Yeah, row axis. So what will be the component? It will be row.
It will
What
be
will be
row.
the unit vector?
I cannot hear it. It will be row.
Yeah, what will be the unit vector?
Yes, Victor. A row.
Arrow. Yes, so it is row arrow. And why it is positive? Because we are considering cylindrical coordinates. So therefore, this is row and my arrow direction will be this direction. This will be the direction of arrow. And since this vector is in the same direction, that is why it is row arrow. And here, this was the AZ direction. And that's why it is minus ZAZ. So this will be row arrow. So therefore, my R vector will be minus Z dash AZ. So going from here to here, minus Z dash AZ plus row arrow, plus row arrow. So this is
Victor,
distance vector. Yes.
I have a question just about one notation. Z
Mhm.
dash. Z dash.
Okay.
Will it differ if I assume it as a Z? And also for DZ, you write it as a DZ dash.
Yeah, you can see what I'm doing is I'm following our Sadiku textbook. So what Sadiku did is whenever you need to do an integration of a source, then Sadiku used a prime instead of just a number. He used a prime. So that's why I'm also using this prime. Now it's up to you. You can remove the prime. Nothing will happen. So for sources, any integration of the sources, he represented it with prime. He represented with prime that like, Z prime or rho prime or D rho prime or DZ prime like this.
Okay, clear, Victor.
So it's just the way that book did so that we don't confuse and always prime represent with respect to the sources. Okay.
Yes, clear.
Now DH. So what is DH? Sorry. So what is DL? So DL bar. So now we need DL bar cross R. So cross product this DL and R cross product. So AZ cross AZ, AZ cross AZ is gone. AZ cross arrow will be, because AZ cross AZ is 0. AZ cross arrow is A5. See, AZ cross arrow is A5 and then DZ dash multiplied by rho. So rho DZ dash. Got it? So now we got DL cross R. So by just cross producting DL vector and R vector. And remember, you should now remember this vector calculus identities. This is 0 and AZ cross arrow is A5. So it is A5. Now put this in our expression. So DH bar is I. What is DL cross R? Rho DZ dash A5. Rho DZ dash A5 divided by 4 pi R cube. What is my R? This is my R. So magnitude of this cube. So magnitude of this will be z dash square plus rho square to the power of half cube. So that's why it is 3 by 2. So this is my magnetic field, which I will see here due to the small elemental length, this one. Now for the complete line, we need to integrate it. So therefore for h bar, we need to integrate it. So what we need to do? We need to integrate it over z dash I rho dz dash a phi over 4 pi z dash square plus rho square to the power of 3 by 2. And from here, we can take the constants outside. So what are my constants? Current, I, because now the integration is with respect to dz dash. So I can take rho outside. So I rho over 4 pi. And can I take a phi outside? Can I take the unit vector a phi outside?
Yes.
Yes. Why? Because a phi doesn't depend on dz dash. A phi doesn't depend on dz dash. So that's why I can take a phi outside. It is unlike other components, and also what you are integrating. You are integrating with dz dash here. So therefore, I can take a phi outside. Now, this is the integration there. So integration over z dash dz dash over z dash square plus rho square to the power of 3 by. Now for this, now you need to go and we need to borrow, the integration methods. And here we have to go and use, the method using trigonometry. So where we assume that tan alpha is rho over z dash. So therefore, z dash will be rho cot alpha. Then you should take care what is dz dash and what is this z dash square plus rho square. And when you substitute all these things, now instead of z dash, we will integrate it in terms of angles. And the angles will be from alpha 1 to alpha 2. And if you do that and simplify, this is the answer that you will get. See, this is the answer. So the answer is h bar is equal to I over 4 pi rho cos of alpha 2 minus cos of alpha 1 times a phi. So now, if you think about it, so how would be this a phi? See here, this was my line, which was carrying the current I, and this was in the z axis, and my observation point was here, and this was my rho, perpendicular distance. So my a phi, so how would be the a phi here in the cylindrical coordinates? My a phi will be, yes, my a phi will be going inside the paper. See, so here you can use the right hand rule. So the right hand rule says that if you put your thumb along the direction of the current, then the curving of the fingers, all 4 fingers, curving of the fingers will give me the direction of the magnetic field. So if you put your thumb towards the current direction, then the curving of my magnetic field is going inside the laptop screen, right? It is going inside the laptop screen. So therefore, my magnetic field will be going inside this laptop screen. So that's why I put a cross. I hope you guys know about these notations. So whenever we put a dot here, that means you are referring a vector which is perpendicular to the screen and which is coming out of the screen. And if we put it a cross mark, that means it's a vector which is perpendicular to the screen, but it is going in the inside the screen. It is going inside the screen. So this is how we represent. So for example, X, Y. Now, if I want to represent Z, I can represent Z like this. So that means my Z is coming out of the plane, out of the screen. So here, the magnetic field A phi is now going inside. Now, if you want to visualize this, and if you put your eye here, so put your eye here. So put your eye here and see. If you put your eye here and see, then this will be my current. Okay, this will be my current. And since there is a dot there, it means that the current direction is outside the screen. So therefore, your magnetic field will be moving in this direction. So this was, you can think that this is my point P. So if this is my point P, then here the magnetic field will be like this. If this is my point P, then the magnetic field will be like this. If this is my point P, then magnetic field will be like this. So your magnetic field will be like rotating, forming circles. See, it forms like a circle. So this is the magnetic field created by the line. And it's a finite line. Remember, it's a finite line. It's not an infinite line because you know both the ends of your line. Now, if we take a special case where our line is semi-infinite, that means one end, if you see here, this is an example. One end is finite. That means I can see this end. But another end is infinite. That means it is going towards infinity. That's why I wrote plus infinity. Then what will be the magnetic field created by this at this point P? What we have to do is we can follow the same, expression that we got for the finite line. Except what we will do is we will just find what will be the angles alpha 1 and what will be the angles alpha 2. So if you remember the definition of the angles alpha 1 and alpha 2, if this is my finite line, okay, so this is my finite line. And if this is my observation point P, then this is my angle alpha 1 and this is my angle alpha 2, right? Clear? This is my angle alpha 1 and this is my angle alpha 2. Now let's apply the same thing here and tell me if this is finite, and if this is my observation point P, then what will be the alpha 1? See here, what will be the alpha 1? Alpha 1 will take 90 degrees. Alpha 1 will take 90 degrees. And what will happen to alpha 2 if you hold this edge of the line and pull it and pull it and take it further. So what will happen to this angle alpha 2? Yes, Ram,
Decrease.
can you tell me? It will decrease. Yes, Mr. Ramzi.
Yes, doctor, it will decrease.
Yes, it will decrease. So when I pull this and take it to infinity, what will be this angle alpha 2 then? It will decrease, and it will? Yes, it will?
It will be 0.
Tend to 0. And at infinity, it will be 0. So these values, if you substitute here, so alpha 2 is 0 and alpha 1 is 90 degrees, then this is I over 4 pi rho A phi. this will be the value for a semi-infinite line. Okay, so h bar is I over 4 pi rho a phi. And what is rho? Remember, rho will always be the perpendicular distance. It's very important. This I also emphasized in the electrostatic case. See, it's the perpendicular distance, not this distance. It's the perpendicular distance. So you have to extend this and find the perpendicular distance between your observation point P and your source. And this is your angle alpha 1 and this is your angle alpha 2. So remember, alpha 2 is the interior angle. See, it is the interior angle. And alpha 1 is the exterior angle. It's not the interior. It's not this inside. It's exterior angle. So based on that, you can get for infinite line also. So here, see, in the infinite line, for the infinite line, we have already seen that if I pull this to infinity, then alpha 2 will tend to 0 and eventually alpha 2 will become 0. In a similar manner, if I take this end of my semi-infinite line, which was at 90 degrees, and then start pulling it, what will happen to alpha 1? Yes, Mr. Abdul Al-Shuair, can you tell me?
What happened to it, Doctor?
What will happen to alpha 1, Mr. Abdul Al-Shuair? So if I hold this end and if I start moving it towards the minus infinity. So if I start moving this towards minus infinity, what will happen?
Become 0, right?
90 degrees. Yes?
It will go to 180.
Yeah, so first you need to identify whether it will increase or decrease, because this is the angle, Mr. Abdullah Shuair, this is the angle. So if I take this end and if I start pulling this end in this direction, then what will happen? This angle will slowly increase. See?
Yes, that's right.
It will slowly increase. And as you move forward, see, it increases further. And when it goes to infinity, your alpha 1 will become
180.
180 degrees. So now if you substitute these two in our finite line equation, so I over 4 pi rho is cos of 0, alpha 2 is, alpha 1 is, alpha 2 is 0 degrees, alpha 1 is 180 degrees. So it is 1 minus of minus 1. So h bar is I over 2 pi rho times a phi. So it will still be going inside the screen. If a phi, it will still be going inside the screen and its magnitude will be I over 2 pi. So for an infinite line, it is I over 2 pi rho. For semi-infinite line, it is I over 4 pi rho. For semi-infinite line, it is I over 4 pi. So change in the magnitude. Direction is the same, a phi and a phi. Okay. Now, you know, these are simple examples. Now, sometimes if you get some a difficult, you know, say type of problem, then in this case, you know, this a phi direction, the a phi direction in which your your magnetostatic field is, this a phi direction. The best way to find this a phi vector is by using the relationship AL cross A rho is equal to A phi. AL cross A rho. And what is your AL? AL is the unit vector along the line current. And A rho is the unit vector along the perpendicular line from the line current to the point of observation. Because it's not necessary that always, you know, your magnetic field will be taking a phi direction. Because if, for example, you use X, Y, Z Cartesian coordinates, then what will be the unit vector? So either you can use your right hand rule and from there you can find out, or use this rule. And this rule says that you just need to, you can easily get it. If this is my line current placed, then if this is my current direction I, then my AL unit vector is in this direction. Then if this is my observation point P, then this is my perpendicular distance rho, and this is my A rho vector. So A rho vector is the unit vector along the perpendicular line. And therefore you can find this magnetic field here at this position. So the direction of this magnetic field will be equal to AL cross A. So you need to find this direction, you need to find this direction, the unit vectors, and if you cross product this, you will get the direction in which your magnetic field is. And again, this is coming from the cross product. Yes, Abdullah.
So, doctor, is this valid also if the line current is on the x-axis or on the y-axis?
Yes. This is valid for every, in any coordinate system. The only thing is, you need to identify in your coordinate system what is your AL and what is your A rho. Okay, what is your AL and what is your A rho? For example, guys, if you put this in Cartesian coordinates, then what is AL? Find out. Then what is A rho? Find out. Cross product this, that will be your direction of your magnetic field. Okay?
Doctor?
Yes.
Why AL is upward, not downward? Like
It is AL takes the direction of your current. So if my direction of the current is upwards, see here, my direction of the current is upwards. So therefore, my AL will take the direction upwards. Okay?
For the previous example, AZ was downward.
Which previous example? Which one you're talking about? This one? No, it was up. See?
No, before.
Here?
Yes, this one.
No, here also it is upward. See?
But AZ was downward.
No, see here, AZ. So it is AZ, positive.
Oh, okay, sorry.
Positive. That means it is going upwards. Positive. Yes. Okay. Now we can take a simple example. So here, this is a good example where how can you find the magnetic field because of two sources. Okay, because of two sources. So if you see here, so two sources are given to you here. One source. So if you see here, there are two sources. So you have one semi-infinite line here and one semi-infinite line here. Now they are put in the Cartesian coordinates. So this is given to you. It is put in Cartesian coordinates. And you are asked to find what is the magnetic field at this point P. And this is 2 meters. This is 2 meters. Okay. And this is one line current and carrying current of 10 amps. And this is the direction. And this is another line current, which is also carrying current 10 amps. And it is in this direction. So how can you find the magnetic field here? So we can find magnetic field here by using superposition. So H bar will be equal to H1 due to line current 1 and then H2 due to line current 2. Because we have seen that electrostatic field follows the superposition principle, magnetostatic field also follows the superposition principle. Okay, now before even starting, can you guys think and tell me what will be the direction of the magnetic field here? What will be the direction of the magnetic field here? You can do it one by one for this line and this line. So for this line, and my observation point is here. So put your thumb along this direction. And where is your curving of your fingers? Your curving of your fingers are going inside the screen, right? Yes. Mr.
Yes, inside.
Yeah, Mr. Ahmed Al-Ghamdi.
Yes.
Yeah, is it going inside the screen if you put your thumb on your line current? If you put thumb here?
Yes, it will go inside the screen.
It will go in. So if you put your thumb here, then your curving of your fingers will be something like this. See? So it will go inside the screen. Okay, now what about this one? Put your thumb here. And my observation point is here. So if I put my thumb here, then what happens to my fingers? Again, my fingers are going inside the screen, right? So both are going inside the screen. That means both this magnetic field H1 because of this current and the magnetic field H2 because of this current, both are going inside the screen. That means it will be in which direction? If this is my X, this is my Y, and my Z is inside the screen. No, it is not inside the screen. Sorry. My Z is outside the screen. So it's a dot. So let me erase and put it properly. So this is my Z. It's a dot. Then your magnetic field is going inside the screen. So that means I can say that my magnetic field has minus AZ component. Clear? It has minus AZ component because from our experience, both are going, they are going inside the screen. So inside the screen. So if this dot, that means my Z axis is coming outside the screen. That means my AZ is outside the screen. Then minus AZ will be inside the screen. So that's why it is minus AZ. So guys, just by analysis, you will know the direction. Now the remaining part left is to find the magnitude. And this kind of analysis becomes very healthy for you, especially when you at least you can eliminate few answers from your multiple choice questions if you have. That at least by finding the direction, you will eliminate 1 to 2 questions, 1 to 2 possible answers. Okay. Now you need to find what will be the magnetic field for this one and what will be the magnetic for this one. So the magnetic field for this one will be, see, for this one. So first join this and join both the ends. Remember, this is going to infinity. And here, this is going to infinity. So this is alpha 2 for this line. And therefore, alpha 2 will be 0. And what will be alpha 1 for this line? Tell me. Yes, can anybody tell me what will be the alpha 1? Yes.
180.
This, no, not 180. This will be alpha 1. You have to find it out.
135.
Yes, it will be 135 because this is 2 meters, this is 2 meters. Then this angle will be 45 and this angle will be 90. So it will be 135. So alpha 1 is 135, alpha 2 is 0. So alpha 2 0, alpha 1 135. So put it here. So you get 0.679 amperes per meter. And guys, see here, I just want magnitude because I already got the direction. So I just want the magnitude. So I'm just substituting in the magnitude. I'm discarding A phi because for my problem statement, I already know what is A phi because in my problem statement, A phi is my minus AZ. Now, what about this case? What about this case? So this is infinity, right? So join this point and then this point. Okay, so this is my current direction. This is my current direction. So which one is my alpha 1 and which one is my alpha 2? So this is my alpha 2, right? And this is my alpha 1. So as this tends to infinity, my alpha 1 goes to 180 degrees. And this alpha 2, we just now found out it is 45 degrees. So substitute alpha 2 is 45 degrees and alpha 1 as 180 degrees, you will get the same answer. Because it will be 10 divided by 4 pi times 2 cos of 45 minus cos of 180 degrees. Okay, so cos of 45 is 1 over root 2. Cos of 180 degrees is minus 1. So minus of minus 1 will be this one. 10 over 4 pi times 2. This will be my H2. And this is same as this one, which is 0.679 amperes per meter. And therefore, my total H will be H1 plus H2. So 0.679 plus 0.679, 1.358. And direction we already found, minus AZ. That's why minus AZ. Got it? So this is how you can do it for lines. Any questions? Okay. Then this is for the line integral. Now, in a similar way, we have one more example where we do it for a ring. Okay, where we do it for a ring. And which is the next lecture. See, here we do it for the ring. Now, how do we do it for the ring? In the same way, see, my observation point is here. Okay, this is my observation point on the z-axis. And the ring is placed in the xy plane. And if it is 0, 0, z, that means this height is z. Now, what do you do here? And this ring is having the current I. So you have to do it in the same way. So this ring has a radius of A. So take a small elemental length dl. But since it's a ring, so you have to go for the cylindrical coordinates and find what is dl in the cylindrical coordinates. So this will be a d phi or r d phi. But r, the radius of the ring is a, so it is a d phi. And again, I'm using dash because it is representing the source. Now, what will be my distance vector? It will be pointing from the source to the observation point. So this will be the direction. From the source to the observation point. This is my R. Okay. So now based on this, again, we can do the same thing. We can first find R bar. So what will be your R bar? Going from here to here, how can you go? So first you go in this direction, and then you go in this direction. So this is minus a arrow, right? Because we are going in the opposite direction of arrow. Arrow direction is this. So minus a arrow, because this is a, and this is z az in this direction. So it is minus rho arrow plus z az. Then what will be my dl? We already got that dl is a d phi dash, and then you can get dl cross r, cross product this, and then you can get the h bar. H bar will be this. So it will have two components. So you have to do both the components one by one. And then you will get this as the answer. So it will be in the AZ direction. Okay. So I think we will stop here. And in the next class, we will take the Ampere's law. So any questions?
Doctor, I have a question.